So here is the Mathcad for a concentric pad footing in cohesionless soils. So some of the assumptions I've stated before in the body of the seminar. So what we're going to be considering here is just two ultimate limit states. That's the long-term bearing capacity failure of the foundation and the long-term sliding at the foundation level. We're not considering earthquake loading. You could do, but that's another exercise. So you need to modify what the loading is and the geotechnical parameters suitable for earthquake loading. So a reminder, long-term analysis is done using effective stress and uses strength parameters, the effective cohesion and the effective angle of shearing resistance. So we begin by putting in our parameters for the footing. So its breadth, its thickness, its length, and the depth to the underside, and the unit weight of the concrete. Then we're putting our loading. So we've got vertical loading and we've got horizontal loading about each direction. And then we put in our soil parameters. So we're saying we're on sandy gravel. So we've got our effective stress cohesion as 0 and our effective angle of shearing resistance as 30. We've got our unit weight of soil and gamma S as 18. But we have an effective weight of soil potentially as 8.1, depending on where your water table is. We can calculate our passive earth pressure, Kp as 3, and that's given in B1 VM2. We can pull out the strength reduction factors for static bearing, passive earth pressure and static sliding pressure, sliding failure from the code. So we start with the total stress and then get the vertical stress in the ground. And because we've got poor water pressure in there, the effective vertical stress is slightly lower than the total stress. We derive our design loadings. Well, first of all, let's work out what the weight of the concrete foundation is, the weight of the backfill above the foundation, and then the resultant, we've got a resultant horizontal load as required. But our resultant reaction, our vertical reaction R, is just simply the sum of the applied load with the weights of the foundation backfill on top. And that's worked out as 48 kilonewtons. So I've recycled the old diagram from the VM4. It's pretty much the same in VM2. And this shows you your plan of your rectangular pad foundation with an eccentric load. And it tells you that part of your pad foundation is effective and another part is not effective. And that's why we have an effective length, L dash, and effective width of B dash. But to calculate those, we need to work out what the eccentricity is. So we've said that the water pressure acting on the underside of the foundation is 4 kPa, so our effective vertical force is reduced because of that poor water pressure. Taking moments about the point load, the eccentricity about the breadth is 79 millimeters, and about the length is about 10 millimeters. So your effective length of the foundation is 880 millimeters. And the effective width is 742 millimeters. You can do a quick check as to whether those dimensions are within the middle third. So compare the L-/2 with the actual dimension over 6, and then we go OK. If we're not, we need to go back and do some adjustment to the size of our pad foundation. So now we look at the effective area of the foundation, A dash, based on the effective width multiplied by the effective length, which gives us a design bearing pressure, i.e. the applied bearing pressure of 68.5 kilopascals. Now this is where we get into complicated calculations, but these calculations are taken from the code VM2. This one is a bit obscure because you're raising the natural logarithm by pi times tan phi and then multiplying it again. So you've got to be careful how you write that to get the correct answer. And if you want, check it against the diagram in the code. So we have NQ, which is worked out as 18.4, NC is 30.1, and N gamma is 20.1. So here are the calculations for the shape factors. Lambda CS is 1.5, lambda QS is 1.48, and lambda gamma S is 0.663. Our ground is level, so therefore all the ground inclination factors are 1. We have our depth factors. Now we have a choice on our depth factors depending on the depth to width ratio. And because our depth to width ratio is less than 1, we take the first value, which gives a gamma QD of 1.23. And lambda CD is worked out based on the lambda QD as 1.25. And lambda gamma D is 1. So our load inclination factors, again, vary depending on which direction you're loading. The horizontal load in one direction, the length, works out as 0.978, and in the width, it works out as 0.675. For convenience, I just take the smallest of those because these numbers are going to be used to multiply your factors together to reduce your potential ground bearing capacity. So then we get to this very long equation, which is given in the code, and you add up all of those numbers and multiply all those factors together, and you get an ultimate bearing strength as 168.1 kPa, which gives you a design bearing strength of 75. Note this is significantly lower than a good ground value. Our capacity divided by our applied load is greater than 1, so we're okay. The next ultimate limit state we need to consider is the long-term foundation sliding failure. So we've worked out that our coefficient of passive earth pressure is 3, and that is going to be used down in our passive resistance. But our sliding resistance is based upon the cohesion under the base, plus the effectively friction underneath the base. So our sliding resistance because of the base is a mere 25.8 kilonewtons. Now, passive resistance, you'll notice the first part of that equation is a simple passive resistance against the face of the foundation. There's this extra factor which is taken from the old version, VM4, and it's given in the example. Now, this doesn't appear in VM2, so if you want to be conservative, take it out, and it'll rework it out as to a reduced capacity. And our C sharp, as it were, our effective cohesion is 0, and therefore our passive resistance works out as 4 kilonewtons. So we've got a design sliding resistance when we put in our strength reduction factors of 22 kilonewtons in length and 22.4 in the width. So in both cases, they're okay. So that's the pad foundation concentric loading for cohesionless